Hi everyone, it's me again, Tasya. In today's video, I will explain the answers for homework 6 about shearing stress at beam. There are two questions here and we are going to analyze it one by one. Okay, without any further ado, let's jump right into question 1. In question 1, there is a built-up wooden beam as shown here with its dimensioning, of course, and it is subjected to a vertical shear of 8 kilonewton. Do not forget to write this down as a note to make the analysis process easier. It turns out that this beam is also attached with nails. You can see the nails here, 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 and so on and so forth. And knowing that the nails are spaced longitudinally every 16 millimeter at A, this one is area A, area A, area A, area A, and every 25 millimeter at B. Sorry for that, I need to delete first. And every 25 millimeter at B. This one is area B, this one is area B. The value of I needed is already given as well, and here is known as Ix. Ix is equal to 1.504 times 10 to the power of 9 millimeter to the power of 4. Once again, do not forget to write those nouns here. And the question, finally, are asking about finding or determining the shearing force, in the nails at A and at B. Okay, now let's start the analysis. Question 1. So since the question asks us to find or determine the shear force at area A and B, so first we need to determine the area of A and B as the step 1. This one, the blue one, is considered as A and the green one is considered as area B. It's just simple actually, just multiplying the base and the height. The base for area A is 50 and the height is 100 here. And if we multiply them, the answer will be 5 times 10 to the power of 3 millimeter square, or 5,000 here. And for area B is the same. It is base multiplied by the height. The base is 300 and the height is 50. So the result is 15,000, or 15 times 10 to the power of 3 millimeter square. I remind you again that the question asked us to determine the shear force, so we need to know the formula for shear force itself, right? So shear force is known to be equal to small q multiplied by s, where the s here is the spacing of the nails that also known in the question, right? Well, for the q, small q is v multiplied by capital Q over I, or inertia. And we also can break the Q down to Q equal to A multiplied by Y. This formula should be done to the area A and area B to find the force at area A and area B. Okay, moving on to the next step, step 2. We need to find the moment of inertia, or Q, capital Q at A. As wrote down here, Q is equal to A multiplied by Y, so for Q at A will be area at A and Y at A. The area at A is already known here, this one. And now we need to find the YA. How do we find it? Is here, YA is the distance between the neutral axis to the centroid of the area A. in here the centroid is in the middle of area A. This one. This one is the centroid of the area A, and it is placed in the middle, right in the middle of the area. So the YA will be the half of 400, which is 200, minus half of the height of area A, which is 100. 100 over 2 will be 50. 200 minus 50 will be 150 millimeter. This one for YA. So we have found the Y, we have known the A, so yeah, we just need to put everything in. Basically, 5 times 10 to the power of 3 multiplied by 150 will be resulted 750 times 10 to the power, sorry for that, 750 times to the power of 10 to time, sorry, 750 times 10 to the power of 3 millimeter cubic, or since we are going to dealing with meter in dimension, so we convert the millimeter cubic to meter cubic. So the moment of area, or Q, at A is 7.5 times 10 to the power of, sorry, the moment of area at A equal to 7, sorry for that. The moment of area, or Q, at A is 7.5 times 10 to the power of minus 4 meter cubic. Step 3 is the same like this, like step 2. The difference is we are going to analyze at area B. At area B, the QB is not only consists of the area multiplied by the Y. Why? It is because at beam B, this one is beam B, is subjected by 3 nails here. The 2 nails are coming from the area A, here, here, and also at B itself. So the moment of area at B will be ABYB plus 2QA. Once again, since the area of B is known, we just need to find the YB. Same like the previous method, we just need to find the distance from the initial axis to the centroid of area B, which is right in the middle of beam B here. So it will be 200 minus the height is 50 over 2, and the YB is 175 millimeter for YB. We just need to put everything in here. Basically 15 times 10 to the power of 3 multiplied by 175 plus 2 times this one, yeah, 750 times 10 to the power of 3. The result in meter will be 4 minus 125 times 10 to the power of minus 3 meter cubic. Now is the next step. The next step, before we jump to the shear force, we need to find the shear flow first. Now is we have to find the shear flow at area A. First, we need to write down the known, the V, the I, and here is the formula to find the shear flow at A, which is the QA, small QA equal to V, capital A over I. The V is known, the I is known, and the QA we obtained from the previous step. We just need to put everything in here, and we obtain the value for QA is 3.99 times 10 to the power of 3 Newton meter. Same step should be done to area B. everything is the same basically. The fee is the same, the I also the same. The difference is only at QB itself. We obtain the QB from step 3. So yeah, we just need to put everything in, and we obtain the QB is 21.94 times 10 to the power of 3 Newton meter. Okay, this will be the last two steps for this question. Sorry. So finally we find the shear force or F at area A first. FA is small qa times SA. S here is the spacing of the nails that is known in the question. At A it is 16 millimeter and QA is this one. We put QA 3.99 times 10 to the power of 3, and the SA is 16 millimeter or 60 times 10 to the power of minus 3 meter. So yeah, finally we found the FA is 239.4 Newton. And this one is the last, which is the shear force at P, the same like the previous question. We just need to put the known here, the QB, this one, and the SB or the spacing for B is 25 millimeter. So we put everything in here and we obtain FB is 548.5 Newton. So the shear force experienced by area A is 239.4 Newton, while area B is 548.5 Newton. Now for the second question, there is a beam and loading shown here, 50 Newton each going down, and the dimension or the shape of the beam will be like this, and this one will affecting the result of the analysis later on. The question asked us to determine the shearing stress at point A, sorry for that, at point A, which is this one, and point B, which is this one. So we just need to jump right into the analysis after this. The analysis begin with step 1, find the reaction forces. Since there are two forces going down here, so the reaction forces will be at RA and at RB here. Two reaction forces as well. RA should be equal to the RB, and we need to find the sigma y. It is assumed that going up will be plus. So sigma y will be RA minus 50 since both of them are going down, plus RB. Since RB is equal to RA, so it will be 2RA minus 100 lah ini. So from here we can obtain the value of RB and equal to RA, of course, is 50 kilonewton. So from this we found the value of V is 50 kilonewton. Also, I forgot to mention here the shape of the beam is like this, and it will be divided into two kind of shape. The first one is this one, the long one, and the second one will be this bottom, which is the white one. The next step is begin with determining the location of the section center. As I mentioned before, that this beam consists of two different shapes, this one and this one. So how we're gonna find the section of centroid is by dividing the sum of a multiplied by y over this one over the sums of a itself. Since there are two shapes, so we have to find at the shape 1 and also shape 2. For shape 1, the y1 is obtained by measuring the distance from the natural axis, or which is the bottom here, to the center of the beam. Here is in the middle, right in the middle of the beam 1. So y1 will be the distance from the base here to this one. Same to the shape 1, shape 2 also measured from the bottom, the base, to the center of the beam here, y2. And to make it easier, we just have to make a table for the area and also the y and the area for a multiplied by y. For area 1, the height is 100 and the base is 225. So the area will be 2500 and the y measured is 100 millimeter. So we multiply them, the answer will be 2.5 multiplied by 10 to the power of 5. For the area 2, the height is 50, the base is 100, so the area will be 5000, and the y measured is 25 millimeter. We multiply them up, and the y multiplied by a is 1.25 times 10 to the power of 5. And then we sum up the area, which is 7500, and we also need to sum up the a multiplied by y, which is 3.75 times 10 to the power of 5. So we just need to put everything here, and the section centroid found is 50 millimeter. And the next step, we have to determine the inertia. The same like the previous step, since we have two different shapes, so we need to find those inertia. The formula of inertia itself for the shape is 1 over 12 bh to the power of 3 plus a d squared. D is found by subtracting the section of centroid to the y, and we make it as absolute value. So if it is found to be minus, the answer will be stay positive. Here we found the D1 is 50 minus 100, which is 50 millimeter, and the D2 is 50 minus 25, which is 25 millimeter. Now we find the total inertia, which is the inertia for shape 1 and shape 2. Basically, we just need to put everything into the formula obtained here to the formula here. And finally, we found that the total inertia is 12.5 times 10 to the power of 6 millimeter to the power of 4. However, since we are going to dealing with meter as the dimension, we need to convert it to meter, and the result is 12.5 times 10 to the power of minus 6 meter to the power of 4. For the next step, we need to find the moment of area, or Q, at A. Here is the figure for the dimension and benchmark. yeah, area A, this one, is known to be, is like pictured to be like this. The green shadow here is the area of A. So how we're gonna find the moment of unit area at A or QA is by multiplying the area of A times the y of A. How we find the YA is by measuring the distance between the section centroid that we have found before, which is 50 millimeter from the bottom. This one is the section of centroid or capital Y to the center of the area A, which is this one. So yeah, the YA is 100 minus 25.2, which is 87.5 millimeter. So we need to put the value of YA here, and for the area A is by multiplying the base by its height. Let me erase this first. The base is 25 millimeter, right? And the height for A is 25 millimeter. So the area, so the area is 25 times 25. And after multiplying those numbers, we obtain the value of QA is 54,687.5 millimeter cube. However, since we are going to deal with meter dimension, so we need to convert that into meter here, and we obtain the value of QA is 5.46875 times 10 to the power of minus 5 meter cubic. So yeah, that's all for the moment of inertia at A. Now moving on to the moment of area at B. Let me erase this first. Area B or point B is known to be here. So the area B is this one, the blue shaded one. How we're gonna find the moment of area at B is same like before, multiplying the area by the y. The y, same like before as well, is the distance between the section of centroid, this one, to the center of area B, this one. So the answer for YA, so sorry, this one is typo. The YB, this one should be YB, is equal to 100 minus 50 over 2, which is 75 millimeter. So we just need to put that into YB here, and to find the area B is by multiplying the base and the height. The base is same is 25, and the height is 25 plus 25, which is 50. So the area is 25, sorry for that, 25 multiplied by 50 here, and the YB is 75. We obtain the number of moment area at B is 93,750 millimeter cube, or in meter will be 9.375 times 10 to the power of minus 5 meter cube. Now is finally we have to find the shear stress at A. So first we need to put the known values first, the V, the I, and T, and then to obtain the value of shear stress at A is by put them into this formula. Actually, for point B and A will be the same for V, I, and T. The difference is only at the Q. The Q obtained from the previous step. So we just need to put the known value here. For V is 50 times 10 to the power of 3. QA is 5.46875 times 10 to the power of minus 5 over DI is 12.5 times 10 to the power of minus 6 multiplied by the T. The T is 25 times 10 to the power of minus 3. So the shear stress at A is 8.75 MPa. The next step is, okay, I made mistake again. The next step is finding the shear stress at B. This one should be B. Okay. Same like before, we wrote the knowns down, this one, and this one, and put them into this formula. Sorry for that. We have to put those into this formula. The difference one is the QB, this one. So yeah, the QB is obtained from the previous step. We put everything in. We put QB here is 9.375 times 10 to the power of minus 5. So the value of shear stress obtained at point B is 15 MPa. So the shear stress experienced by area A is 8.75 MPa, while area B is 15 MPa. That is all for the explanation for homework 6. I know there are many flaws from the explanation, but I need your suggestion, of course, for better explanation next time, better video next time. Thank you for watching and see you later.